Now, I will be sharing a quick explanation about Newton's law of motion and how they connect to linear motion in our daily lives. To start, Newton introduced three important ideas about how objects behave. The first idea is basically about inertia. Things don't just start or stop moving on their own. Something has to cause that change. So, if a ball isn't rolling, it's because no force has acted on it yet. His second idea explains the link between force, mass, and acceleration. When you push something lightly, it moves slowly. Push harder, it speeds up more. But if the object is heavy, you need more force to get it moving. This is where the famous formula F equals to ma comes from. The third idea is about action-reaction. Whenever you apply a force, there is always a force pushing back in the opposite direction. A simple example is when you jump, the ground actually pushes you upward.
Now I will explain the mechanisms that are related to a car movement. Firstly, we have Newton's first law, or inertia. A car will not move unless something pushes it, and it will keep moving straight at the same speed unless something slows it down, like friction or brakes. Next, according to Newton's second law, which is force and acceleration, a car accelerates because the engine produces a force, and acceleration depends on the total force. F equals to ma. Therefore, more engine force means faster acceleration, while a heavy car results in slower acceleration. After that, we can look at Newton's third law, which is action-reaction. When the car engine turns the wheels push on the road, and the road pushes the car forward with an equal and opposite force. The action is the tires pushing the road backward, and the reaction is the road pushing the car forward. Furthermore, static friction occurs at the tire grip. This grip lets the tires push the road so the car can move forward. Meanwhile, kinetic friction occurs when a car is skidding, when the tires slide on the road, and this friction slows the car down. In addition, there is air resistance. The faster the car goes, the stronger the air pushes against it. This air resistance slows the car down unless the engine is strong enough to fight it. Then, we also have impulse or braking force. The brakes apply a force over time, and this force slows the car down. Lastly, a car's movement is also influenced by momentum. A moving car has momentum, which depends on its speed and weight. A fast or heavy car has more momentum, so it's harder to stop. Momentum only changes when something pushes or slows the car, like brakes or friction. In conclusion, all these mechanisms work together to explain how a car moves and how it slows down.
Okay, move on to related figure to support your justification. Linear motion of a car. This figure shows all the force acting on a car as it moves in a straight line. At the top, we have a normal force, which is an upward force from the ground. At the bottom, we have the weight mg of a car acting downward due to a gravity. On the right side, the arrow represents the driving force F, engine, produced by the engine which is push the car to move forward. On the left side, we have the air resistance and frictional force which oppose the car motion. The interaction between these forces determine whether the car speeds up, slows down, or moves at constant velocity. Let me show the relationship between displacement versus time graph. From graph A shows a stationary car explained by Newton's first law since no net force acts on it. Next, graph B shows constant velocity also explained by Newton's first law because balance force allow the car to maintain uniform linear motion. Lastly, graph C shows acceleration which is caused by unbalanced force according to Newton's second law. These three graphs illustrate how Newton's law governs all forms of linear motion from rest to constant speed to acceleration. Next, I will show the relationship between velocity and time. The velocity versus time graph of a car directly reflect Newton's law of motion. When the car accelerates along the upward line, an unbalanced force acts on it, demonstrating Newton's second law. When the car moves at constant speed, horizontal line, all forces are balanced, showing Newton's first law. When the car brakes and slows down, slanted down line, a net backward force acts on the car, again explained by Newton's second law and supported by Newton's third law through the tire and rod interaction. This stage shows acceleration, uniform motion, and deceleration. Then it represents key behavior in linear motion. Now let me explain about Newton's third law at tire and rod contact. This diagram illustrates how Newton's third law explains when the car forward motion. When the car tires rotate, they push backwards against the rod. That is the action force. In response, the rod pushes the car forward with the equal and opposite traction force. This forward traction force is what actually drives the car ahead. As long as the reaction force is greater than the opposing force like friction and air resistance, the car accelerates in a straight line. So essentially, the car moves forwards because the tire pushes backward on the rod, and the rod pushes forward the car with an equal and opposite force.
In conclusion, our presentation shows that Newton's laws of motion are the foundation of understanding how a car moves in a straight line. These laws explain why a car can stay at rest, how it accelerates when force is applied, and how it slows down when an opposing force acts on it. We also saw the linear motion is not just about moving forward, it involves changes in speed, velocity, and acceleration. Important forces like friction, air resistance, momentum, and impulse all play a major role in influencing the movement and control of a car. By understanding this concept, we can clearly see how physics applies to real-life situations, especially in analyzing car behavior and improving road safety. Here's the list of references.